In this video, we'll find the electric potential at some point at a distance d above a uniformly charged wire. So the differential electric potential is equal to 1 over 4 pi by the permittivity of free space by the differential charge on the radial distance from that charge to the point where we're determining the electric potential. Now the differential charge can be written as the linear charge density by dx. And using Pythagoras, we can find the radial distance from that differential charge to the point where we're trying to determine the electric potential. So if we take the origin, x equals 0, at the start of the wire, well, from the origin of the wire to dq, we have a distance of x. And therefore we can use Pythagoras' theorem to determine r as root x squared plus d squared. So therefore we have 1 over 4 pi epsilon naught by lambda dx on the square root of x squared plus d squared. So now if we integrate over the length of the wire, then what we're effectively doing is summing up the differential potential due to those infinitesimal charges all along the wire, from x equals 0 to the length of the wire. So that's equal to the electric potential at this point. Now we can take the constants outside the integral, so we have lambda on 4 pi epsilon naught by the integral from 0 to L, and we're integrating root x squared plus d squared with respect to x. And now we can use trigonometric substitution to evaluate this integral. So if we take this as theta, then tan theta is x on d, and x can be written as d tan theta. And therefore the differential dx is equal to d sec squared theta d theta. And now let's rewrite this integral over here. So if we make the substitution for x and dx, well, what we get is d sec squared theta d theta in the numerator. And that's divided by the square root of x squared, which is d squared by tan squared theta, and then plus d squared. So we factor out d squared and put a 1 here. And now we can use a trig identity. So remember that cosine squared theta plus sine squared theta is equal to 1. So if we divide through by cosine squared theta, then what we get is 1 plus tan squared theta is equal to sec squared theta. So what we have effectively is the integral of d sec squared theta d theta. And in the denominator, we have root d squared, which is d, and tan squared theta plus 1 is sec squared theta, and taking a square root we get sec theta. So therefore we can see that the d's cancel, and sec theta is also going to cancel, so we're integrating sec theta over theta, and what this gives is the natural log of sec theta plus tan theta. And now we can substitute for sec theta and tan theta. So what we get is the natural log of sec theta. So remember that cos theta is equal to d on r. So sec theta is r on d. And tan theta is opposite on adjacent, so that's x on d. So we just add x over here. And we can also substitute for r into here. And that's our integral evaluated. So what we obtain is lambda on 4 pi epsilon naught. And we've evaluated this integral as a natural log of the square root of x squared plus d squared plus x on d. And this is being evaluated from x equals 0 to x equals L. So what we get is lambda on 4 pi epsilon naught by the natural log of root L squared plus d squared plus L on d. and then minus the natural log, and if we substitute 0 into here, well, what we get is root d squared on d, which is d on d, which is 1. So we get the natural log of 1 here. And the natural log of 1 is 0, so that cancels out. And therefore, this here is our final electric potential. So we can just take this out and the natural log of 1 out. And I'll see you in the next video.